Hello and welcome to 5.10, where we're going to talk a little bit about how you actually separate enantiomers from a racemic mixture into their individual parts. And this is important because there are a lot of molecules that are interesting or useful to us as humans if they are in single enantiomer samples, but as a racemic mixture, they're either useless or basically dangerous. So what we need to do is, or as scientists, is turn a racemic mixture into pure enantiomer samples, and that's called resolution of enantiomers, just the separation of a racemic mixture into um, the enantiomers separated from each other. One of the most common ways to do this is by separation, or sorry, crystallization. And in crystallization, um, you are making crystals of chemicals from a solution. You might have done this in a Gen Chem lab, or perhaps in organic chem lab if you were in those this semester. Um, Basically, um, with with resolution of chiral species, you are doing the crystallization with a chiral molecule. So you could start with some kind of molecule like an amino acid. Say this is alanine, and you have its enantiomer as well. And if you take these two chemicals and you put in some acid that is also chiral, like let's say let's see what is let's say we use something like malic acid. Let's draw this up here. There we are. If you take malic acid, you can have a protonation like this that makes diastereomers of each of these molecules. Like this one, for example. And diastereomers have different chemical properties than enantiomers do. And if you make a diastereomer, then you can do a much easier separation, such as by crystallization or some other means. And this is really key to make a diastereomer because, as we said before, and as in your book, enantiomers themselves have the exact same chemical properties. So you cannot separate them typically by normal chemical means because their boiling point, melting point, and how they interact with other molecules typically is the exact same. So making a diastereomer is really key if you want to resolve enantiomers. And remember, this kind of went just with itself. We didn't draw the other one for the other, we didn't draw diastereomer formation for the other enantiomer. Okay, the other one we're going to talk about is much less common, but it is also useful, and that's called column chromatography. So imagine with me that you have a glass tube, okay, a long glass tube with a little nozzle at the end there. And in that glass tube, in between two porous supports, is some kind of material. We'll just color it yellow. Okay. In this material, if you could zoom in way far, so we're going to zoom in here. If you could zoom into the material, what it would look like is all these tiny spheres of slightly different sizes. Filling that tube where it was yellow. And if you could zoom in onto each individual sphere, we're going to call this zoom in. There we are. If you could zoom into every individual sphere, what you would see is that the surface of each individual sphere, which was made up of silicon oxide like glass, also has onto it some kind of chiral material, like this. Like this alanine, for instance. I'm drawing alanine because it's the easiest, but it's not always alanine. And so, because on the surface of each little particle is a chiral agent, and this material is made up of these little particles, all smushed together in this giant tube, then you can put in some molecule on the top here. Like let's say you put in a solid sample here, and you dissolve it in some solvent that it's good with. It could be water or some other organic solvent. And if you do that, as this goes through the column, because gravity will force it to come down, so as it goes through the column, depending on what type of enantiomer it is, your molecule here, some molecules, some enantiomers that we are trying to separate, will either interact strongly, and so it'll go pretty slow, as you're seeing me do here, where it just kind of slowly flows down the column, slowly, or you could have the case where maybe it doesn't interact very much at all. And so then it goes very quickly down through the column, much faster. And so you can collect one first and then the other. That's the basics of chromatography anyway. And these are the two main ways that we have to separate enantiomers from racemic mixtures, and the individual components, such as the alanine that we drew here, or the malic acid that we drew here, are called resolving agents because they help to resolve enantiomers from racemic mixtures. And this has been section 5.10.